I mean, these tiny, almost imperceptible interactions happening deep inside atoms actually dictate, well, pretty much everything.
It sounds wild, doesn't it?
Yeah. Like how we keep global time with pinpoint accuracy, how we map the most distant corners of the cosmos, and even how we're shaping the future of computing.
It really does sound like science fiction sometimes.
But it's pure, astonishing quantum mechanics at play.
Exactly.
Today, we're embarking on a deep dive into something called hyperfine transitions. And this isn't just about the atom's basic structure, the stuff we might remember from school.
No, not at all. We're going much deeper.
We're exploring the absolute finest, most delicate details of atomic energy levels, way beyond what most people typically imagine.
Right.
Our mission here is to guide you through the quantum foundations, the really surprising physics, and the incredible real-world applications of these minute atomic interactions.
And hopefully make it clear without being overwhelming.
Exactly. By the end, you'll feel genuinely well-informed, and I promise you'll be armed with some facts about how these subtle quantum effects shape our entire world that will absolutely blow your mind.
Sounds like a plan.
Okay, let's unpack this a bit. When we talk about an atom's energy levels, it's really like looking at a finely woven tapestry, right?
Yeah.
With layers of incredible detail.
That's a great analogy.
You start with what we call the gross structure. That's the big picture, the basic electrical attraction between the electrons and the nucleus.
A dominant part, yeah.
Then, if you zoom in a bit closer, you start to see the fine structure.
Uh-huh.
This is where things get a little more complex, accounting for effects like relativity and how an electron's own tiny magnetism interacts with its motion around the nucleus, spin-orbit coupling and all that.
Right, relativistic effects,
Yeah.
spin orbit,
Yeah.
those corrections.
But if you were to zoom in even further, using incredibly high-resolution techniques, that's when you uncover the hyperfine structure.
This is where we're headed today.
It's an even deeper, far more subtle splitting of those already finely divided energy levels.
And subtle is the key word.
Oh yeah, we mean it. These hyperfine energy shifts are typically, 1,000 times smaller than those from the fine structure?
About that, yes. Roughly a factor of 1,000 smaller. It's truly a quantum whisper.
Wow. So what's actually causing this whisper?
Well, what's truly fascinating here is that the origin of this hyperfine structure isn't just about the electrons themselves or, how they're arranged.
Okay.
It's genuinely about the direct electromagnetic interaction between those electrons and the atomic nucleus itself.
The nucleus. So not just the electrons talking to each other.
No, it's electron nucleus. We're
Yeah,
talking
okay.
about a very intimate coupling between the nucleus's own tiny magnetic and electric properties.
Properties of the nucleus.
Exactly. We call these its multipole moments. Primarily, it's magnetic dipole and electric quadrupole moments.
Okay, dipole and quadrupole.
And the fields generated by the electron cloud right at the nucleus. This interaction provides us with a direct window into the nucleus's intrinsic properties, like its spin, its magnetic moment, even its charge distribution.
So it's like we're peering right into the heart of the atom.
That's precisely it. We're probing the nucleus via the electrons.
That's incredible that the electrons are essentially sensing what's happening right inside the nucleus. But why specifically these two types of moments, a magnetic dipole and electric quadrupole? Are there others that just don't count?
That's an excellent question. It actually comes down to fundamental symmetry principles in quantum mechanics.
Symmetries again.
Always. Particularly something called parity conservation. These principles basically dictate which types of nuclear properties can effectively interact with the surrounding electrons in this specific way.
Do they rule things out?
They do. For instance, they strictly forbid other moments, like an electric dipole or a magnetic quadrupole, from having a significant interaction. It just doesn't happen based on symmetry.
Okay.
So the magnetic dipole is the simplest, sort of lowest order magnetic interaction allowed.
Makes sense.
And the electric quadrupole is the next simplest electric interaction that's allowed by these fundamental rules. They establish a clear hierarchy.
Got it. So nature simplifies things for us a bit there.
In a way, yes, it limits the complexity.
So if we clarify the main players in this quantum dance then,
Yeah.
you have the nucleus, which has its own intrinsic angular momentum, like a tiny quantum spin, which we call nuclear spin, symbol I.
Right, the nuclear spin I.
And then the electrons have their own total angular momentum, J, which is a combination of their orbital motion and their own spin.
That's J, exactly. L plus S gives you J.
So are there any atoms where this hyperfine dance just doesn't happen, like at all?
Absolutely. And here's a crucial condition for that. Hyperfine structure only exists if the nucleus has a non-zero spin quantum number.
Okay.
So if that nuclear spin I is greater than 0, if I is 0, no hyperfine splitting of this magnetic type.
Which nuclei are like that?
Well, common examples are helium-4, carbon-12, oxygen-16. They all have I0.
So no hyperfine for them.
Yeah. Their nuclei are essentially perfectly spherical, magnetically speaking, and don't have that magnetic moment to interact with the electrons in this way.
Got it. So for the nuclei that do have spin, that tiny magnetic interaction between the nucleus and the electrons actually couples their individual angular momenta, I and J.
Right. It links them together.
To form a new combined conserved quantity, the total angular momentum of the entire atom, which we call F.
F, yes. The total atomic angular momentum.
And this F is simply the vector sum of J and I.
Correct. F equals J plus I.
And just like everything else in the quantum world, the magnitude of F is quantized. It takes on specific integer or half-integer values, ranging from the absolute difference Ji all the way up to J plus I.
Exactly, a range of possible F values.
And for each possible value of F, you get 2F plus 1 magnetic quantum numbers, MF, ranging from -F to plus F, just like with J and MJ.
Precisely the same mathematical structure for angular momentum.
Okay, so how does this coupling actually lead to the energy shifts? You mentioned Hamiltonian.
Right. We describe the energy shifts using the hyperfine Hamiltonian, HHFS. The main contributor, the biggest piece of this, comes from the magnetic dipole interaction.
M1.
M1, yes. This arises from the nuclear magnetic dipole moment interacting with the magnetic field created by the electrons right at the nucleus.
Okay.
Now, what's really interesting is that this electron-generated magnetic field actually has several distinct physical origins.
Oh, it's not just one thing.
No. There's a contribution from the electron's orbital motion, moving around the nucleus.
Like a current loop.
Sort of, yeah. And there's a contribution from its intrinsic spin dipole moment, the electron's own magnet.
Makes sense.
But the truly unique and often dominant contributor, especially for atoms like hydrogen and the alkali metals, is the Fermi contact interaction.
Fermi contact, that sounds important.
It is. This isn't really a classical interaction you can picture easily. It arises from the direct interaction of the nuclear magnetic moment with the electron spin density right at the nucleus's position, literally overlapping.
So it's about the electron actually being inside the nucleus, probability-wise.
Essentially, yes. The probability density at R0, it's only non-zero for subshells, electrons with zero orbital angular momentum, because they're the only ones with non-zero probability right at the center.
Ah, okay, so only for S electrons.
Primarily, yes. And in many simple atoms, it's the largest part of the hyperfine interaction. It's a very precise measure of how much the electron's magnetic personality is right there inside the nucleus.
So it's like the electron spin is literally touching the nucleus's spin. That's a fantastic image. Is there anything else contributing to these tiny shifts?
Yes, there's also the electric quadrupole interaction, E2.
E2, okay.
This only comes into play if the nucleus itself isn't perfectly spherical.
Like if it's stretched or squashed.
Exactly. If it has a nuclear spin I of 1 or greater, it can have a non-zero quadrupole moment. It basically characterizes how much the nucleus's charge distribution deviates from being a perfect sphere.
Like a little football or a pancake shape.
Precisely. And this non-spherical nuclear electric quadrupole moment then interacts with the gradient of the electric field from the electrons at the nucleus.
The gradient, so how rapidly the field changes.
Yes, the spatial change in the electric field. While this E2 term is usually smaller than the M1 magnetic dipole term, it provides invaluable information about the nucleus's actual shape, which is amazing to get from such a tiny interaction.
Definitely. So even with no external fields messing things up, these two interactions, M1 and maybe E2, cause the energy levels to split.
That's right, even in isolation.
What's the key takeaway about how a single atomic level, maybe one defined by J, breaks down into these finer hyperfine levels?
Okay, so in a zero-field environment, it's primarily the magnetic dipole interaction, the M1 term, that causes the splitting.
Right.
It's nicely described by the Landau-Interval rule. This equation basically shows how a single fine structure level with a particular J value actually splits into a multiplet of distinct hyperfine energy levels. Yes, one level for each possible value of the total atomic angular momentum, F.
So F determines the specific hyperfine levels.
Correct. Think of it like this. What looks like a single line in a lower resolution spectrum isn't just one line. It's actually a tightly packed set of several lines, each representing a unique way the nucleus and electrons can subtly align their spins relative to each other.
And how many lines are in that set?
The number of these unique sublevels is determined by both I and j. It's typically 2i plus 1 if I is less than or equal to j, or 2j plus 1 if j is less than I. Basically, the smaller of the two spins determines the multiplicity.
That's a super clear way to put it. Okay, just to sum up this first part before we add fields, what's the fundamental difference between the fine structure and this even more subtle hyperfine structure?
Yeah, good recap. Fine structure is primarily about the electron's own properties, relativistic effects, their spin coupling to their orbit. It's an intra-electron thing, a correction to the basic electron-nucleus energy. Hyperfine structure, however, is a step deeper. It's the electromagnetic interaction between the electrons and the nucleus itself.
Ah, so nucleus involved.
Directly involved. Fine structure deals mainly with electron properties within the atom's fields, while hyperfine structure brings the nucleus's own magnetism and shape directly into the interaction.
And the energy scale.
Vastly different. Hyperfine shifts are typically about 1,000 times weaker, 1,000 times smaller energy differences than fine structure shifts, much more subtle.
Right. Okay, makes sense. So now, here's where it gets really interesting, I think. What happens when you apply an external magnetic field?
Ah, yes, the Zeeman effect.
This field fundamentally changes how these energy levels behave, right?
It does. The atom's behavior then depends critically on how strong this external field is compared to the atom's own internal hyperfine coupling strength.
So it's a competition.
Exactly, a competition between the internal coupling and the external field. To really understand it, we think about the atom's total energy Hamiltonian. It now includes the original atomic energy, the fine structure, the hyperfine structure.
Take 0 HFS, HHFS.
Right, plus this new term, Hz, for the external Zeeman interaction, the interaction of the atom's total magnetic moment with the external field.
Okay, so how does this competition play out? Are there different scenarios?
Definitely. We can identify 3 distinct field regimes, each with its own unique behavior, and importantly, its own set of good quantum numbers to describe the states.
Okay, regime 1.
First, the low field regime. This is often just called the Zeeman effect for hyperfine structure. Here, the external magnetic field is relatively weak.
How weak?
Weak meaning the energy shift it causes, EgZ, is much smaller than the hyperfine energy splitting, Fs.
So the internal coupling wins.
Pretty much. In this scenario, the hyperfine coupling between the nuclear spin I and the electronic angular momentum J remains strong. They essentially stay locked together to form F. So F and its projection MF are still considered good quantum numbers. They describe the state well.
And the energy shift?
The energy shift here is simply linear with the field strength. It's proportional to B times MF. Each hyperfine level F splits into a neat set of 2F plus 1 equally spaced Zeeman sublevels, each labeled by a unique MF.
Like gently pulling apart the already split hyperfine levels.
Exactly that. A nice, predictable, linear splitting.
Okay, what happens if we crank up the field?
Right. Now move to the high field regime. This is known as the Paschen-Back effect for hyperfine structure.
Paschen-Back.
Here, the situation flips entirely. The Zeeman energy from the external field now dominates the internal hyperfine interaction. A is much larger than F's.
So the external field wins big time.
It does. The strong external field acts like a powerful magnet that effectively decouples I from J. It breaks their internal coupling.
They ignore each other now.
In a sense, yes, they no longer care about each other in the same way, which means F is no longer a useful quantum number. It's not conserved anymore.
So what are the good quantum numbers?
Instead, I and J simply precess independently around the strong external field. The states are better described by their individual projections, MJ and MI.
The uncoupled basis.
Exactly, the uncoupled basis. The energy shift is predominantly from these uncoupled moments interacting with the field, plus a small correction that still lingers from the now weakened hyperfine interaction, usually proportional to MI times MJ.
Wow, so a complete breakup of that internal quantum relationship.
Pretty much, yeah. A drastic change in behavior.
So you have these two extremes. Either the nucleus and electron are totally coupled, low field F is good, or completely uncoupled, high field MI and MJ are good. What happens in between? That sounds like chaos.
It does seem like it would be messy, right? The intermediate field regime, where the Zeeman energy is comparable to the hyperfine splitting, neither interaction dominates.
So F isn't good, but MI and MJ aren't quite right either.
Exactly. Neither simple picture works perfectly. Generally, you'd have to diagonalize the full Hamiltonian matrix numerically to find the energy levels.
Which sounds complicated.
It can be. But remarkably, for atoms with electronic angular momentum J12, which includes the ground states of hydrogen and all the alkali metals, incredibly important atoms,
Okay.
an analytical exact solution exists.
Really? A formula for the messy bit.
Yes. This is the celebrated Breit-Rabi formula. It elegantly describes the nonlinear way the energy levels depend on the magnetic field strength right through this tricky intermediate regime.
That's amazing. What does it look like?
If you were to plot these energies versus the magnetic field strength B, you get a beautiful Breit-Rabi diagram. It visually depicts this continuous transition from the coupled Zeeman levels at low field to the uncoupled Paschen-Back levels at high field.
So it shows the whole evolution.
Precisely. And a key feature you see in these diagrams is the non-crossing rule levels that have the same total magnetic quantum number, which is MF in the low field limit and MI plus MJ in the high field limit, simply do not cross as the magnetic field changes.
They repel each other.
Effectively, yes. It's a fundamental quantum mechanical principle related to perturbation theory.
So the Breit-Rabi formula is like the ultimate GPS for these atomic energy levels, showing them shift and curve as we dial up the magnetic field. How does it manage to connect those two very different scenarios, Zeeman and Paschen-Back?
That's exactly what it does. The Breit-Rabi formula is truly the mathematical bridge connecting the two limits.
How so?
If you take the formula and look at its form for very weak fields, where the field strength parameter is small, it simplifies, and you recover the linear Zeeman effect for the coupled states, depending on F and MF.
Right.
Conversely, if you look at it for very strong fields where the field parameter is large, it simplifies again, and this time it recovers the Paschen-Back splitting for the uncoupled states, depending on MI and MJ, plus that small MI-MJ correction term.
Wow. So it smoothly transitions between them.
Perfectly. It depicts the continuous evolution of the atom's fundamental quantum states and their energies as the external magnetic field strength is varied. It's really a testament to the predictive power of quantum mechanics.
That's fantastic. Okay, quick summary then. Low fields, the atom's internal IJ coupling holds. F is good, nice linear splitting. High fields, the external field dominates, breaks the coupling. MI and MJ are good, Paschen-Back splitting. And in between, for J12 anyway, the Breit-Rabi formula guides us through that nonlinear transition.
You've got it. That's the essence of how external fields affect hyperfine structure.
Okay, so we know these levels exist and how they shift. Now, how do these atoms actually talk to us? How do they reveal these subtle energy differences?
Right. How do we see transitions? Well, transitions happen when atoms interact with electromagnetic radiation. They absorb or emit photons.
Light, essentially.
Or, in this case, usually not visible light. The photon's energy has to precisely match the energy difference between the atomic levels involved in the transition. Photon exist. And because these hyperfine splittings are so incredibly tiny, the energy differences are very small. This means the transition frequencies fall into the radio frequency, RF, or microwave range.
Ah, so not optical light, but radio waves or microwaves.
Exactly. Wavelengths typically from centimeters up to meters. Much longer wavelengths, lower frequencies, lower energies than optical transitions.
Now, are there rules about which transitions can happen? Like, can an atom jump between any two hyperfine levels if you hit it with the right microwave frequency?
No, not just any transition is allowed. There are strict selection rules, just like for other types of atomic transitions. When we talk about transitions between hyperfine levels, it's critical to understand the rules for magnetic dipole M1 transitions.
M1 again. Why M1 specifically?
Okay, so the strongest, most common type of atomic transition is usually an electric dipole E1 transition. These are responsible for most of the bright spectral lines we see. But E1 transitions have a strict requirement. They need a change in parity between the initial and final states. Parity is related to the symmetry of the electron's wave function, essentially its orbital shape.
Okay. Parity change needed for E1.
Yes. But hyperfine transitions happen within the same electronic configuration. The electron's orbital state, L, and spin state, S, don't change. Only the relative orientation of J and I changes. So the parity stays the same.
Ah, so E1 transitions are forbidden between hyperfine levels.
Exactly. Because there's no parity change, electric dipole transitions between hyperfine sublevels of the same electronic state are strictly forbidden.
So because the strong E1 transitions are forbidden, the weaker M1 transitions become the way these levels communicate.
Precisely. This is why M1 transitions, even though they are significantly weaker by a factor related to the fine structure constant squared, roughly 1137.2 compared to E1 transitions, become so crucial for observing hyperfine structure. They do not require a parity change.
Okay, so M1 is the key. What are the selection rules for these M1 hyperfine transitions?
The rules are derived directly from angular momentum conservation, remembering that the photon itself carries 1 unit of quantum spin.
Right, spin one particle.
So the rules state that the change in the total angular momentum quantum number, AF, must be 0 or 1.
A equals 0, 1.
And the change in the magnetic quantum number, AF, must also be 0 or 1.
MF equals 0, E away, AE. Okay. Are there any other restrictions?
Yes, a couple of very specific and important ones. First, a transition from an F0 state to another X0 state is strictly forbidden.
F0 to F0 is impossible. Why?
It comes down purely to angular momentum conservation. You simply can't combine an initial state with 0 angular momentum, S00, with a spin 1 photon and end up with a final state that also has 0 angular momentum, F0. It's like vector addition. 0 plus 1 cannot equal 0.
Makes perfect sense. What's the other restriction?
Also, a transition where both FS0 and F0 simultaneously is forbidden for M1 transitions. You can have AF0, AS0, or F00, AO1, but not both 0 at the same time.
Got it.
And just for those interested in the experimental side, the MS0 transitions, often called transitions, are driven by an oscillating magnetic field that's parallel to the main quantization axis, the direction of the external B field, usually.
Okay.
While the MS1 transitions, called sus transitions, are driven by a rotating or circularly polarized magnetic field that's perpendicular to that axis. This determines how you actually drive the transition in the lab.
Fascinating. Now, you said M1 transitions are much weaker. What does that imply for, say, how long an atom stays in an excited hyperfine state?
That's a crucial point. Because M1 transitions are so incredibly weak, their probability of occurring spontaneously is very, very low.
Right.
And that translates directly into unbelievably long natural lifetimes for these excited hyperfine states. I mean, the most famous example, as you mentioned earlier, is the ground state hydrogen atom. Its F1 excited hyperfine state has a natural radiative lifetime against decaying to FS0 of about 10 million years.
10 million years. That's genuinely mind-boggling. It barely seems like a transition at all.
Exactly. This is precisely why they're often called forbidden transitions in spectroscopy. They're not truly forbidden by symmetry like the E1 case, but they're so improbable they might as well be in many lab contexts. They can happen, but only very, very slowly on their own.
Okay, but if the natural lifetime is millions of years, how do we even see these lines in experiments or in space? Are spectral lines really that sharp?
Ah, that's the catch. You're right, a 10 million year lifetime implies an incredibly narrow natural line width, almost zero width. But in most real-world settings, whether it's a gas cell in a lab or diffuse gas clouds in astrophysics, the observed width of a spectral line is usually not determined by this natural lifetime broadening.
It's broadened by other things.
Exactly. It's dominated by other, much faster processes. The most common culprits are Doppler broadening, which comes from the thermal motion of the atoms. Atoms moving towards you seem higher frequency, away seem lower, smearing the line.
Right, the temperature effect.
Then there's pressure broadening, or collisional broadening, which comes from atoms bumping into each other. These collisions interrupt the quantum state and shorten its effective lifetime, broadening the line.
Makes sense.
And especially in experiments where you have atoms flying through a measurement region, like an atomic beam, there's transit time broadening. This is just due to the finite time the atom spends interacting with your measurement apparatus. If it flies through too quickly, Heisenberg's uncertainty principle kicks in, relating time and energy uncertainty.
So even though the natural line is razor thin, these other effects usually make it look much wider.
Precisely. So achieving high-precision spectroscopy of hyperfine transitions really becomes an exercise in clever experimental design aimed at mitigating or eliminating these other broadening effects. You need to cool the atoms down, isolate them, and watch them for a long time to reveal that true, incredibly narrow quantum whisper hiding underneath.
Got it. So when we think about atoms talking, the strong E1 transitions are like a loud shout, but they're forbidden here. For hyperfine, we're listening for a much quieter M1 whisper. And that whisper is surprisingly long-lived naturally, even if it's often drowned out by other environmental noise like temperature and collisions.
That's a perfect summary. And to actually observe and, more importantly, manipulate these incredibly minute energy splittings and transitions, We've had to develop a really sophisticated suite of experimental methodologies over the decades.
It's not just point-and-shoot spectroscopy anymore.
Oh, far from it. We've moved way beyond just passively observing spectral lines with better spectrometers. Modern experiments now actively control the atoms. We use techniques like laser cooling to prepare ultra-cold samples, optical pumping to initialize atoms into specific quantum states, and also to read out the final state.
Oh.
And precisely timed microwave or radio frequency fields to coherently drive transitions between the hyperfine levels. It's become a complete toolkit for quantum state preparation, manipulation, and measurement.
Allowing us to harness these subtle properties for some really advanced applications, I imagine.
Absolutely. That's where it gets really exciting.
Okay, let's talk about some of those techniques. One foundational method must be magnetic resonance spectroscopy, right? Like NMR and EPR.
Yes, definitely. Electron paramagnetic resonance, or EPR, sometimes called electron spin resonance, ESR, is a key technique.
What's that used for?
It's primarily used for species that have unpaired electrons. Think free radicals, many transition metal ions, defects in solids, things with a net electron spin.
Okay. How does it work?
The basic principle is pretty straightforward. You put your sample in a strong, static magnetic field. This field splits the energy levels associated with the electron spin, the Zeeman effect for the electron spin.
Right.
Then you irradiate the sample with microwaves. When the microwave frequency precisely matches the energy splitting between the electron spin levels, the electrons absorb energy, and you detect that absorption.
Okay, that sounds like standard resonance. Where does Hyperfine come in?
The real analytical power of EPR often comes directly from the hyperfine interaction itself. If there are nuclei nearby the unpaired electron that have their own nuclear spin...
Like protons or nitrogen nuclei.
Exactly. Those nuclear spins interact with the electron spin via the hyperfine coupling. This interaction further splits the electron spin energy levels.
So the lines you see get split again.
Yes. Instead of seeing just one line for the electron spin flip, you see a pattern of multiple lines. It's like a tiny ripple or a fine structure on top of the main electron Zeeman splitting caused by the nearby nuclei.
And what can you learn from that pattern?
A huge amount. For example, the number of lines in the pattern tells you how many equivalent nuclei are interacting with the unpaired electron. A classic textbook example is the methyl radical, UCH3.
Okay.
It has one unpaired electron interacting with 3 equivalent protons, each with spin I12. The EPR spectrum shows a beautiful 1.3.3.1 quartet of lines. That pattern directly tells you there are 3 equivalent protons.
Wow, just from the line count and intensity.
Exactly. And the spacing between those lines gives you the hyperfine coupling constant, usually called A. This A value is directly proportional to the electron spin density at the nucleus.
So how much the electron is visiting that nucleus?
Precisely. It's a direct measure of how delocalized the unpaired electron is, which tells you about bonding and molecular structure.
That's incredibly informative. Anything else?
Yes. If the interaction is anisotropic, meaning the splitting depends on how the molecule is oriented relative to the magnetic field, you can get incredibly detailed information about the molecule's precise geometry and the nature of the orbital the unpaired electron is in.
You can tell shape from it too.
You can. And there are even more advanced techniques like ENDOR, electron nuclear double resonance, and HACE score that allow you to measure very small hyperfine couplings or couplings to many different nuclei with much higher resolution. EPR is a really powerful tool.
Okay, so that's EPR for electron spins. What about NMR, nuclear magnetic resonance? Doesn't that usually deal with non-magnetic molecules?
Standard NMR, yes, typically looks at diamagnetic molecules where all electrons are paired. But NMR can also be incredibly useful when applied to paramagnetic systems molecules that do have unpaired electrons.
How does that work? How does the electron affect the nuclear spins?
Well, the strong magnetic moment of the unpaired electron dramatically alters the NMR spectrum of the nuclei within the molecule. That electron-nucleus hyperfine interaction shows up in 2 main ways in the NMR spectrum.
Okay, what are they?
First, you get massive hyperfine shifts. The resonance frequencies of the nuclei are shifted enormously compared to where they'd be in a non-magnetic molecule, sometimes by hundreds or even thousands of parts per million.
Huge shifts. What causes them?
They have 2 main origins, both related to the hyperfine interaction. There's the Fermi contact shift, directly related to the unpaired spin density right at the nucleus.
Like at EPR.
Exactly. And there's the pseudo-contact shift, which is a through-space dipolar interaction that depends on the molecule's geometry and the magnetic anisotropy of the electron spin.
So the shifts tell you about spin density and structure.
Yes. The second effect is paramagnetic relaxation enhancement, or PRE. The rapidly fluctuating magnetic field from the nearby unpaired electron provides a very efficient way for the nuclear spins to relax, to return to their equilibrium state.
So it affects the signal lifetime.
Yes, it significantly shortens the relaxation times, T1 and T2, of the nuclei, which leads to much broader NMR lines for nuclei close to the paramagnetic center.
So you get shifted lines and broad lines.
Right. By carefully analyzing these shifts and the line broadening, researchers can literally map electron spin density across a molecule, determine precise geometric structures, especially in complex systems like metalloproteins. It turns the problem of paramagnetism into a powerful analytical tool.
Very clever. Okay, beyond magnetic resonance, what about using light or microwaves more directly?
Absolutely. We can use high-resolution laser spectroscopy. Modern tunable lasers have incredibly narrow line widths, much narrower than most atomic transition widths. This allows them to directly resolve the hyperfine structure of optical transitions. So you're not looking at the transition between hyperfine levels, but at how the hyperfine interaction splits the upper and lower levels involved in a transition you excite with visible or UV light.
Ah, okay. You see the splitting in the optical spectrum.
Exactly. Techniques like saturated absorption spectroscopy or laser-induced fluorescence can measure these tiny frequency intervals in the optical spectrum with extremely high precision, allowing us to determine the hyperfine coupling constants A for M1 and B for E2 very accurately.
So lasers give us the fundamental constants.
They are a key tool for that, yes. And then there's optical pumping. This is a really versatile and incredibly sensitive technique, fundamental to many modern atomic physics experiments.
Optical pumping, what does that involve?
It uses resonant light, usually circularly polarized, to selectively excite atoms out of certain ground state magnetic sublevels, MF states. Imagine you shine, say, right circularly polarized light plus light onto a vapor of alkali atoms. This light can only excite atoms that follow the dim as F+1 selection rule.
All right.
As these excited atoms decay back down, they can fall into various ground state sublevels. But because you keep exciting out of specific sublevels, over time you get a net transfer of population. Atoms accumulate in the sublevels that don't absorb the sub plus light.
So you create an imbalance.
Exactly. You create a population imbalance among the ground state hyperfine sublevels. You essentially polarize the atomic vapor, aligning the atomic spins.
And how do you detect that?
You can often detect this polarization simply by monitoring how much of the pumping light is transmitted through the vapor. As the atoms get pumped into non-absorbing states, the vapor becomes more transparent.
Okay.
Now, here's the clever part. If you then apply a radio frequency or microwave field that is resonant with the transition between these populated and unpopulated ground state sublevels, it drives transitions, redistributing the atoms and destroying the polarization you created. This causes a sudden increase in light absorption.
Ah, so the microwaves change the light absorption.
Yes. This technique is called optical RF double resonance or optical microwave double resonance. It uses the sensitivity of optical detection to see a tiny microwave transition. It's the basis for many highly sensitive atomic magnetometers and was crucial in the development of early atomic clocks.
That's really elegant, using light to see microwaves.
It is. And of course, microwave spectroscopy itself directly probes the transitions between hyperfine levels. You can measure the direct absorption of microwaves, or you can couple it to an optical probe beam for enhanced sensitivity, like in the double resonance method.
And in modern experiments.
In modern quantum experiments, particularly with cold atoms, we use optical pumping extensively for preparing atoms in specific initial hyperfine states and also for reading out the final quantum state after some manipulation. And we use precisely controlled microwave pulses for the coherent, high-fidelity manipulation of hyperfine qubits. They are essential tools in the quantum control toolbox.
Okay, so we have these amazing tools, but you mentioned earlier that things like Doppler broadening are a major limitation for precision. How do we beat that?
Right. Getting to the ultimate precision requires tackling those broadening mechanisms head-on. And the biggest enemy for high-resolution spectroscopy of free atoms is usually Doppler broadening, caused by their thermal motion.
Because moving atoms see shifted frequencies.
Exactly. If atoms are zipping around randomly, the spectral line gets smeared out. The key breakthrough here was laser cooling and trapping.
Cooling atoms with lasers. How does that even work?
It sounds counterintuitive, right? Shining light on something usually heats it up. But by using carefully tuned lasers interacting with specific atomic transitions, you can arrange for atoms moving towards a laser beam to preferentially absorb photons and get a momentum kick slowing them down.
So the light acts like a brake.
Precisely. By using multiple laser beams from all directions, you can create what's called optical molasses, dramatically slowing down the atoms in all 3 dimensions. This reduces their temperature from room temperature down to the microkelvin regime, or even nanokelvin.
Wow, incredibly cold.
And at those temperatures, the Doppler broadening is virtually eliminated. You can start to see the true, narrow spectral features.
That's amazing. What about trapping them?
Once the atoms are ultra-cold, we can confine them in space using various types of traps. The most common is the magneto-optical trap, or MOT, which uses a combination of laser beams and magnetic fields. There are also purely optical traps, like optical dipole traps, that use focused laser beams to hold the atoms.
And why trap them? Just keeping them cold isn't enough.
Trapping allows for incredibly long observation times. Instead of an atom just whizzing through your apparatus in milliseconds, you can hold it and interrogate it for seconds, or even longer in some cases.
Yeah.
This dramatically reduces that other broadening effect we mentioned, transit time broadening. Long observation time means narrow lines.
So cooling gets rid of Doppler, trapping gets rid of transit time.
That's the core idea. This combination of laser cooling and trapping is truly the foundational technology for virtually all modern high-precision experiments with neutral atoms. It underpins the best atomic clocks, quantum simulators, and many fundamental physics measurements.
Are there other techniques to push precision even further?
Yes. Building upon cold atoms, we have things like atomic fountains.
Fountains, like spreading atoms upwards.
Essentially, yes. You take a cloud of laser-cooled atoms from a MOT and gently launch them vertically upwards inside a tall vacuum chamber. They travel up, turn around under gravity, and fall back down. On their way up, and again on their way down, they pass through a microwave cavity where the crucial interrogation happens often using that Ramsey method we discussed for clocks.
2 passes through the cavity.
Right. The long flight time in free fall, up to a second or so between the 2 microwave interactions, allows for incredibly long interrogation times. This leads to exceptionally narrow spectral lines for the hyperfine transition.
And that's how the best clocks work.
This atomic fountain geometry is the basis for most of the world's primary frequency standards, the most accurate atomic clocks we have today.
Amazing. What about ions? Can you do this with charged atoms?
Yes. For charged particles, we use ion traps. These use combinations of static and oscillating electric and magnetic fields to confine just one or a small number of ions in a tiny region of space, basically indefinitely.
Holding a single atom.
Or a few, yes. Once trapped, these ions can also be laser-cooled, potentially even down to their absolute motional ground state within the trap. This allows for exquisite quantum control over their internal hyperfine states and their motion.
Any applications?
Ion traps form the basis for some of the most precise atomic clocks currently operating, competing with neutral atom fountains. They are also one of the leading platforms for building scalable quantum computers, using the hyperfine states of the trapped ions as qubits.
Incredible control. Okay, let's make this really concrete now. Let's look at some truly amazing real-world examples where hyperfine transitions are not just lab curiosities, but central players.
Absolutely. Case study 1 is a perfect example.
This involves a profound shift in how we define time itself. Back in 1967, the definition of the second, our fundamental unit of time, was completely changed.
A huge moment in metrology.
We stopped relying on astronomical observations, basically, watching the Earth spin and orbit the sun, which isn't perfectly regular.
Right, it slows down, wobbles.
And instead, we redefined the second based on the immutable, perfectly stable, hyperfine transition of the cesium-133 atom.
A move from the heavens to the atom.
That's a massive leap in precision and stability, right?
Yeah.
Going from planetary motion to the quantum world inside a single type of atom.
Absolutely. And the choice of cesium-133 wasn't arbitrary. It turns out to be practically ideal for timekeeping for several reasons.
Okay, why cesium?
First, its atomic structure. Cesium is an alkali atom like sodium or potassium. It has a single valence electron in its outermost shell, the 6s electron. This makes its electronic structure relatively simple, with the ground state having LO0 and J12, no fine structure complications in the ground state.
Simple's good.
Simple is very good here. Second, its nucleus, the stable isotope cesium-133, has a relatively large nuclear spin, I-72.
I-72, okay.
This large nuclear spin couples with the electron spin J12 to create two very well-separated ground state hyperfine levels, F3, which is the lower energy state, and F4, the higher energy state.
Two distinct levels.
Yes. And the energy difference between these two levels corresponds to a transition frequency in the microwave range, which is convenient experimentally. And because cesium is a heavy atom, the interaction is quite strong, leading to a high frequency. Precisely 9,192,631,770 hertz.
Wow. That's the definition, exactly that many cycles per second.
That is the definition of the second. 1 second is the duration of exactly 9,192,631,770 periods of the radiation, corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom.
Incredible.
And that very high frequency gives the transition a very high quality factor, or Q factor. Q is frequency divided by line width. High Q means high stability and precision for timekeeping.
So high frequency helps precision.
Greatly. Plus, just practically, cesium metal has a low melting point and a good vapor pressure at reasonable temperatures, making it relatively easy to work with in a laboratory vacuum system. It ticks all the boxes.
Okay, so cesium's the perfect atom. How does a modern cesium fountain clock actually use this transition to keep time so precisely? Walk us through it.
Right. A modern cesium fountain clock is a marvel of engineering. It works roughly like this. First, you start with cesium atoms, laser cool them down to microkelvin temperatures, and trap them in a MOT.
Step 1. Get them cold and trapped.
Step 2, launch. You gently launch this cold cloud upwards into a tall, shielded vacuum tube like a fountain.
Okay.
Step 3, state preparation. As they start their flight, a precisely timed laser pulse makes sure all the atoms are in one specific hyperfine ground state, let's say the lower F3 state.
Get them all set up.
Step 4, Ramsey interrogation. As the atoms fly upwards through a carefully designed microwave cavity, they receive a precisely timed microwave pulse, a 2-pulse. This doesn't cause a full transition, but puts each atom into a coherent quantum superposition of both the F3 and F4 states.
A mix of both.
Yes. Then they continue flying up, reach the peak of their trajectory in the dark, shielded region, and fall back down. As they pass through the same microwave cavity on the way down, they receive a second identical 2-pulse.
Why 2 pulses with a wait in between?
That's the Ramsey method. The final state of the atom after the second pulse, whether it ends up in F3 or F4, depends extremely sensitively on the phase difference accumulated between the two states during the free flight time. And that phase difference depends directly on whether the microwave frequency was exactly resonant with the atomic transition frequency.
So it's super sensitive to being slightly off frequency.
Exquisitely sensitive. The longer the flight time, the more sensitive it becomes. Step 5, detection. After the second pulse, a laser beam probes the atoms to measure the fraction that ended up in the upper F4 state, or the lower F3 state.
Count the atoms in each state.
Essentially, yes. Step 6, feedback loop. The measurement signal, how many atoms made the transition, is used to generate an error signal. This error signal is maximized when the microwave frequency is perfectly on resonance. This signal is fed back to the microwave source, constantly steering its frequency to stay locked precisely onto the cesium atomic reference frequency.
So the atoms tell the electronics exactly what frequency to be.
That's exactly it. The locked microwave output provides that incredibly stable standard frequency, which is then divided down electronically to produce the standard 1 pulse per second output.
The impact of this is just, it's hard to overstate. How accurate are we talking here? What is that number 9 billion hertz really buy us?
We're talking accuracy at the level of parts in 1016, or even slightly better now with the latest generation fountains.
10 to the 16. What does that mean in real terms?
It means these clocks would lose or gain only about 1 second in over 300 million years.
300 million years. That's insane.
It's an almost unimaginable level of precision. And this precision is absolutely foundational to our modern technological world. Think about global navigation satellite systems like GPS or Galileo.
Right, GPS needs accurate time.
Critically, your GPS receiver works by measuring the tiny differences in arrival times of signals from multiple satellites. Since those signals travel at the speed of light, An error of just a few nanoseconds, billionths of a second in the timing, translates directly into meters of error in your calculated position. The atomic clocks on the satellites and in the ground control stations make GPS possible.
Wow. Okay, what else?
It synchronizes global telecommunication networks, the internet backbone, digital television broadcasts, even national power grids rely on this precise timing for stability.
The internet runs on atomic time.
In a very real sense, yes. Financial markets rely on microsecond-level timestamping for high-frequency trading regulations.
All right.
And beyond technology, these clocks are incredible tools for fundamental physics. They allow extremely stringent tests of Einstein's theory of general relativity. For example, you can measure the gravitational redshift time running slower at lower altitudes just by lifting a clock by a few tens of centimeters.
Just lifting it changes its tick rate measurably.
Yes. They're also used in searches for potential time variation of fundamental constants, like the fine structure constant, and even to look for interactions with exotic physics, like dark matter. They are probes of the very fabric of space-time.
It really is a cornerstone of our modern world, built on a quantum transition inside cesium.
Absolutely, a hidden quantum engine driving so much.
Okay, let's pivot now to our second case study. This is almost the flip side of the coin. From defining terrestrial time with exquisite precision using cesium, we're moving to mapping the entire cosmos using humble hydrogen.
The most abundant element in the universe.
And this involves, as you mentioned earlier, a truly remarkable paradox. A transition so incredibly weak and slow, that 10 million year lifetime, that it would be almost useless in a typical laboratory setting.
Right. Virtually impossible to see spontaneously in the lab.
Becomes one of the most powerful beacons for tracing the vast, diffuse clouds of hydrogen gas that permeate the entire universe. That's genuinely mind-boggling. How does that work?
It absolutely is a fantastic story. We're talking about the famous 21-centimeter line of neutral hydrogen.
The 21-centimeter line.
As we discussed, the ground state of a neutral hydrogen atom, Hi, has an electron with spin J12 and a proton with spin I12.
Electron and proton spins.
Their tiny magnetic interaction splits this single ground level into two very closely spaced hyperfine levels. The F1 state, where the electron and proton spins are essentially aligned, parallel, which is slightly higher in energy.
F1, aligned, higher energy.
And the F0 state, where their spins are anti-aligned, anti-parallel, which is slightly lower in energy.
F0, anti-aligned, lower energy.
A spontaneous transition from the upper F1 state down to the lower F0 state involves the electron effectively flipping its spin relative to the proton. It's a spin flip transition.
Okay.
This is an M1 magnetic dipole transition, and as we know, M1 transitions are intrinsically weak. In this case, it's extremely weak, highly forbidden.
The 10 million year lifetime one?
That's the one. The energy released in this transition is minuscule, about 5.9 microelectron volts. This corresponds to a photon with a very specific frequency, 120.40575 megahertz.
1.4 gigahertz.
Right in the radio part of the spectrum. And the wavelength is about 21.1 centimeters, hence the 21-centimeter line.
Okay, so the paradox again. How does something so incredibly weak, so slow, become so important astrophysically? If an atom only emits a 21-centimeter photon once every 10 million years on average, how can we possibly see enough of them?
That's the key insight. The extreme weakness, the long radiative lifetime, is actually irrelevant in the conditions of interstellar space.
How so?
In the diffuse interstellar medium, ISM, the density is incredibly low, but it's not zero. Hydrogen atoms occasionally bump into each other or other particles. These collisions happen much, much more frequently than the spontaneous radiative decay typically. An atom might experience a collision every few hundred years or so.
Collisions are way faster than the decay.
Way faster. And these collisions are very effective at exchanging energy and flipping the spins. This means the relative populations of the F1 and F0 states are primarily determined by collisions, not by radiation. They quickly reach thermal equilibrium with the kinetic temperature of the surrounding gas.
So the levels get populated according to the gas temperature.
Exactly. The ratio of atoms in the F1 state to the Fu0 state acts as a direct thermometer for the temperature of the cold, neutral hydrogen gas clouds in space. Even though each atom emits very rarely, there's just so much hydrogen out there, and the collisions keep repopulating the upper state according to the temperature.
So we see a steady glow at 21 centimeter, whose brightness tells us about the temperature and amount of neutral hydrogen.
Precisely. The long radiative lifetime, which would make the transition practically unobservable in a lab experiment due to realistic observation times, becomes completely unimportant in the vastness and timescale of the cosmic environment. Instead, the faintness means the transition is rarely optically thick. The photons usually escape the gas clouds easily. It makes this faint signal an incredibly robust tracer of the bulk neutral hydrogen in the universe.
So it's a whisper that, because there are trillions upon trillions of atoms whispering over cosmic time, and because collisions keep them talking, becomes a detectable cosmic hum.
That's a perfect way to put it, a cosmic hum at 21 centimeters.
And what has listening to that hum told us about the universe?
Oh, it completely revolutionized radio astronomy and our understanding of our own galaxy and the cosmos. Firstly, mapping the galaxy.
How did it help with that?
Visible light from distant stars in our Milky Way gets blocked by vast clouds of interstellar dust. We can't see through it optically to map the galaxy's structure, but 21-centimeter radio waves pass right through that dust unimpeded.
Radio sees through dust.
Exactly. So, by tuning radio telescopes to 1420 millihertz and mapping the sky, astronomers could trace the distribution of neutral hydrogen, HI, throughout the entire Milky Way disk, revealing its spiral arm structure for the first time.
Seeing the galaxy's shape in hydrogen.
Yes, and even more importantly, by measuring the tiny Doppler shifts of the 21-centimeter line coming from different directions.
The frequency shifts due to motion.
They could determine the velocities of these gas clouds. This allowed them to trace the Milky Way's rotation curve, how fast things orbit the galactic center at different distances.
Okay. And what did that show?
The expectation based on the visible stars and gas was that rotation speeds should decrease at large distances from the center, following Kepler's laws. But the 21-centimeter observations showed that the rotation curves remained surprisingly flat, or even rose slightly, way out in the galactic halo where there's very little visible matter.
Things are moving too fast.
Way too fast. This discrepancy was the first compelling observational evidence for the existence of dark matter. It showed that most of the mass in our galaxy and others isn't in the stars and gas we can see, but in some invisible, non-interacting substance, dark matter, forming a massive halo around the visible disk.
Wow. The 21-centimeter line discovered dark matter, essentially.
It provided the first really solid kinematic evidence for it on galactic scales, a completely unexpected and revolutionary discovery driven by listening to hydrogen's hyperfine whisper.
That's incredible, but what about even further out in cosmology?
Its role in cosmology is potentially even more profound, though technically much more challenging. We're talking about 21-centimeter cosmology.
Probing the early universe.
Yes. Specifically, it's the only known direct probe of the universe during the cosmic dark ages.
The Dark Ages.
This is the period after the cosmic microwave background, CMB radiation, was released, about 380,000 years after the Big Bang, but before the first stars and galaxies formed and lit up the universe maybe a few 100 million years later. During this time, the universe was filled mostly with smooth, neutral hydrogen and helium gas, and it was dark.
Okay.
The 21-centimeter signal from that neutral hydrogen, although incredibly faint and redshifted by cosmic expansion to much lower frequencies today, meter wavelength, carries information about the density fluctuations and temperature variations in the gas during that epoch.
So it's a snapshot of the universe before stars.
Exactly. It potentially holds pristine information about the initial conditions laid down by cosmic inflation, complementary to what we learned from the CMB. It's a unique window into that crucial, unexplored era.
And what about when the first stars did form?
That's the other key cosmological application, probing the epoch of reionization, EO1.
Ionization, when the universe became ionized again.
Yes. As the first stars and galaxies ignited, their intense ultraviolet radiation started to ionize the surrounding neutral hydrogen, creating expanding bubbles of hot ionized plasma within the still mostly neutral intergalactic medium.
Okay.
The 21-centimeter signal provides a way to map this process in 3D and over time. Neutral hydrogen outside the bubbles produces a 21-centimeter signal, though modified by the radiation fields, while the ionized hydrogen inside the bubbles does not.
So you see the bubbles growing.
Precisely. By observing the 21-centimeter signal at different frequencies corresponding to different redshifts or cosmic times, we can potentially create a movie of reionization, watching how these ionized bubbles grew and eventually overlapped, transforming the universe from neutral back to the ionized state we see today.
That sounds incredibly powerful. What are the challenges?
Oh, the challenges are immense. The cosmological 21-centimeter signal is incredibly faint, maybe millions of times weaker than the radio emission from our own Milky Way and other foreground sources.
Buried in noise.
Deeply buried. Separating that faint cosmological signal from the overwhelmingly bright foregrounds is a major data analysis challenge. Plus, for ground-based telescopes, terrestrial radio frequency interference, RFI, from TV stations, FM radio, satellites, etc., contaminates the very frequencies we need to observe.
Our own noise gets in the way.
Massively. This is a major motivation for proposals to build next-generation low-frequency radio telescopes on the far side of the moon, which is uniquely shielded from Earth's RFI.
Going to the moon to hear the universe's dawn. Amazing.
It highlights how important the signal is considered for understanding our cosmic history.
Okay, so from cesium clocks defining our second to hydrogen mapping dark matter and cosmic dawn. If we connect this to the bigger picture now, looking towards the future, it seems these hyperfine principles aren't just for fundamental science anymore. They're right at the cutting edge of advanced technology development.
Absolutely. There's a remarkable synergy emerging.
What do you mean by synergy?
Well, as we've seen, hyperfine states can be ingeniously selected or engineered to be incredibly insensitive to certain kinds of external fluctuations, particularly magnetic fields if you choose the right states.
Clock states.
Exactly. That insensitivity makes them excellent candidates for storing quantum information robustly for quantum computing qubits.
Okay, so
Yep.
stable for quantum info.
But other hyperfine states, or the same states used differently, can be made predictably and exquisitely sensitive to those same fluctuations, like magnetic fields via the Zeeman effect.
Right.
And that predictable sensitivity makes them perfect for building ultra-precise quantum sensors. So you have this duality. Stability for information, sensitivity for sensing, often using the very same atomic systems.
That's a really neat way to put it. Let's dig into the quantum computing aspect first. How are hyperfine states used as qubits?
It's one of the leading approaches. The basic idea is to choose two distinct hyperfine sublevels within the ground electronic state of an atom or ion. For example, two specific FMFA states. These two stable levels then serve as the computational basis states, your quantum 0 and 1 or.
Simple enough. What are the advantages of using hyperfine states?
The biggest advantage is their potential for exceptional coherence. Because these are levels within the electronic ground state, they don't suffer from spontaneous decay like optically excited states do.
Right. Long lifetimes.
Very long intrinsic lifetimes. Plus, the nuclear spin component is relatively well isolated from stray electric fields in the environment, which are often a major source of decoherence for other types of qubits. This combination leads to extremely long coherence times, how long the quantum state can survive before getting scrambled.
How long are we talking?
In trapped ion systems using hyperfine qubits, coherence times exceeding 10 minutes have been demonstrated. That's an eternity in the quantum world.
10 minutes. That's incredible.
And as we mentioned, the existence of those special clock states is another huge plus. If you choose your 0 and 1s states to be two levels with MF0 in different F manifolds, like the cesium quark transition, the transition frequency between them is, to first order, completely insensitive to fluctuations in the external magnetic field. Since magnetic field noise is often the dominant noise source in these experiments, using clock states makes the qubits exceptionally resilient.
Building in noise immunity.
Exactly. This combination of long coherence and built-in resilience is why hyperfine qubits are the workhorse for several leading quantum computing platforms.
Which one specifically?
They are heavily used in trapped ion quantum computers, using ions like ytterbium-171 or barium-137 or Barrow, which have nuclear spin I-12 or I-32 respectively.
Okay.
And they are also central to neutral atom quantum computers and simulators, often using alkali atoms like rubidium-87 or cesium-133, the same atom used in clocks. These platforms trap arrays of hundreds or even thousands of neutral atoms, using optical tweezers and use lasers and microwaves to manipulate their hyperfine qubits.
So really foundational for quantum tech.
Absolutely, a key enabling resource.
Okay, so on one hand, hyperfine transitions give us these incredibly stable qubits by exploiting insensitivity. But you also mentioned the flip side, using their sensitivity for sensors. Tell us about high-precision magnetometry.
Right. If you choose hyperfine states where MF is not 0, their energy shifts linearly with the strength of an external magnetic field due to the Zeeman effect. We saw that in the low field regime.
E proportional to B times MF.
Exactly. So if you can measure that energy shift very precisely, you can determine the magnetic field B with incredible accuracy.
How do you measure the shift that precisely?
A very common and sensitive method is, again, based on Ramsey spectroscopy, similar to the atomic clocks.
Okay.
You start by using optical pumping to prepare the atoms in a specific initial MF state. Then you apply a microwave 2 pulse to create a superposition of that state and another MF state.
Put it in a superposition.
Then you let the atoms evolve freely for a set time t in the presence of the unknown magnetic field B. During this time, the quantum phase of the superposition evolves at a rate proportional to the energy difference between the two states, which in turn is proportional to B.
So the phase winds up based on the field strength.
Precisely. After time t, you apply a second 2-microwave pulse. This pulse effectively converts the accumulated phase difference into a measurable population difference between the two MF states.
Phase becomes population.
Yes. Finally, you use an optical probe beam to measure the final populations, often via fluorescence or absorption. The measured population difference tells you the phase accumulated, which tells you the magnetic field B.
And how sensitive can these atomic magnetometers be?
They are among the most sensitive magnetic field sensors ever developed. Sensitivities routinely reach the femtotesla FT level, which is 10 Tesla. For comparison, the Earth's magnetic field is about 50 microtesla, 5 by 10 or, and the fields generated by human brain activity are down in the femtotesla range.
Wow, sensitive enough to measure brainwaves.
Exactly. That's one of the major application areas. Magnetoencephalography, MAG, using arrays of these atomic magnetometers, often operating in a shielded room, to non-invasively map the tiny magnetic fields produced by neural currents in the brain. It gives excellent temporal resolution of brain activity.
Amazing. Other applications?
Yes, they're used in geophysical surveying for detecting subtle magnetic anomalies associated with mineral deposits or underground structures. Also in fundamental physics searches, looking for exotic spin-dependent interactions predicted by some theories beyond the standard model, or searching for permanent electric dipole moments of fundamental particles, which would violate fundamental symmetries. They are incredibly versatile, high-precision tools.
From quantum computing to mapping the brain. That's quite a range. Is there a connection to everyday medical imaging like MRI?
There is, actually, though it's a bit more indirect. The role of hyperfine coupling in magnetic resonance imaging, MRI, comes in through contrast agents.
Contrast agents, the stuff they inject sometimes.
Exactly. MRI itself is based on nuclear magnetic resonance, NMR, detecting the transitions of nuclear spins, usually the protons in water and fat molecules within the body, when placed in a strong magnetic field.
Okay, standard MRI is nuclear spins.
Yes. But to enhance the contrast between different tissues or to highlight specific features like blood vessels or tumors, patients are often administered a contrast agent. The most common ones contain paramagnetic metal ions, typically gadolinium-3 or GeDO.
Gadolinium? Why gadolinium?
Gadolinium-3 is used because it has a large number of unpaired electrons, 7 of them, in fact giving it a very large magnetic moment.
Okay.
When this GeDO complex circulates in the body, its large fluctuating magnetic moment interacts strongly with the nuclear spins of the surrounding water protons. This interaction is a form of hyperfine coupling, mainly through space dipolar coupling, but also potentially some scalar contact coupling.
Ah, the electron spin talking to the proton spin again.
Yes. And this electron-nuclear interaction provides a very efficient pathway for energy exchange. It dramatically increases the rate at which the water-proton nuclear spins relax back to their thermal equilibrium state after being excited by the MRI machine's radio frequency pulses.
It makes them relax faster.
Much faster. Specifically, it shortens both their longitudinal relaxation time, T1, and their transverse relaxation time, T2.
Okay, T1 and T2 get shorter. How does that create contrast?
In many common MRI sequences, particularly T1-weighted images, tissues where T1 is shorter appear brighter. So when the gadolinium contrast agent accumulates in certain tissues, like highly vascularized tumors or in the blood vessels, the water protons that relax much faster, their T1 becomes very short, and those tissues light up brightly on the MRI image.
So the gadolinium makes things pop.
Exactly. It highlights the areas where it concentrates. And the effectiveness of a contrast agent, its ability to shorten T1 and T2, is quantified by a property called relaxivity. This relaxivity is fundamentally governed by the strength and dynamics of that electron-nuclear hyperfine coupling between the gadolinium electron spins and the water-proton nuclear spins.
So hyperfine coupling is the hidden physics behind why MRI contrast agents work.
That's a great way to summarize it. It's a crucial, though often unstated, element in this vital medical technology.
Wow, what an incredible journey this has been, really. We've traveled all the way from understanding hyperfine structure as just a subtle correction in atomic energy levels, these tiny quantum whispers,
Seemingly insignificant at first glance,
to seeing how they become a phenomenon with truly profound and incredibly far-reaching consequences across science and technology. The theoretical framework itself is so elegant, described by the Hamiltonian, those different interaction terms, and that beautiful Breit-Rabi formula connecting the different regimes.
It really shows the power of quantum mechanics to describe these intricate details. And the principles governing the transitions between these levels, especially the surprising utility we found for those intrinsically weak and technically forbidden M1 transitions?
Yeah, the forbidden ones turned out to be key.
Absolutely. Perfectly exemplified by the cesium-133 atomic clock. That M1 transition now defines our very notion of time, the second, and underpins so much of our global navigation and communication infrastructure.
And then there's the 21-centimeter line of hydrogen, using another M1 transition, a true cosmic beacon that allows us to map our own galaxy through the dust, peer back into the universe's earliest, darkest epochs.
Revealing the first compelling evidence for dark matter, and potentially letting us literally watch the universe light up during reionization, all from a spin flip.
And today, the precise control and manipulation of hyperfine transitions stands firmly at the frontier of quantum technology.
It really does.
The remarkable isolation from the environment and potential for incredibly long coherence times make them premier candidates for qubits in quantum computers, driving progress in leading platforms like trapped ions and neutral atoms.
Building the future of computation on these stable states.
While simultaneously their exquisite sensitivity to magnetic fields, when harnessed correctly, allows us to create atomic magnetometers of unparalleled precision.
With applications ranging from mapping human brain activity with MEG, to searching for new fundamental physics, to aiding geological exploration.
It truly demonstrates a recurring theme in physics, doesn't it? That the most subtle, most nuanced phenomena occurring at the deepest quantum level often turn out to have the most transformative and enduring impact on our scientific understanding and our technological capabilities.
It's a beautiful illustration of that. Sometimes the smallest details hold the biggest secrets and the greatest potential.
Which really raises, I think, an important final question for you, our listener, to ponder.
What other quantum whispers might still be out there, waiting to be heard or harnessed? Hiding in plain sight, perhaps, within the fundamental laws of the universe as we currently understand them, or maybe just beyond our current ability to detect or control.
And what transformative impact might they have on our future understanding and capabilities if and when we do learn to listen to them? It makes you wonder what else is waiting in the subtle details.